Now we move into testing the SPI core utilizing the accelerometer, the ADXL. So let's see that program. Okay, so the program is called a G sensor check. And if you go and check it to see what it actually does, you'll see it actually defines a few constants. So that read command is actually the command we've seen before, which is actually 0B. Remember, the write command is 0A and the read command was 0B. It also tells me the part ID register, which is register number 2. This is the one that should return FE or F2 actually. This is just to check that the part is actually working, and then the data register for X is 8, and then the 9 and 10 will be automatically generated. So this is the one that is actually interesting. So row max is 127 divided by 2. And what the range for this accelerometer is plus minus 2 Gs. So it's actually the maximum amount you get is 2 Gs and the minimum amount is minus 2 Gs. This is by default. You can definitely change this, but we're just going to utilize the default. So in order for us to report these results as basically in terms of Gs, in terms of how many gravity, like the force, how many Gs, what we need to do is we need to divide it by some sort of a normalization factor. So this normalization factor tells me it takes 127, and 127 is the maximum of 8 bits signed number. So the maximum of 8-bit signed number is 127, and this represents the plus 2G. So if we divide it by 2, basically the number you get is actually 1G. So that number you have, which is a float number, is actually how much is in 8 bits, how much is that row 1G. So if you take that number and you divide, like for example, you read the X or the Y and you divide it by this number, the ultimate result is actually in terms of G's, not in terms of row numbers. Okay, so we move on in here. We have like a few variables in here. So we set the frequency, even though it's set by default to 400 Hertz, but we just basically, we're not changing anything because the constructor for that driver sets it up to 400 Hertz. And then we set it to mode 0 by setting the C-pol and C, the polarity, the C-pol and the C phase. And then the first thing we did is actually assert the slave select. And since we only have one, we just basically, that's the only one we're using, which is the accelerometer, which basically is at 0. And then let me show you that particular graph. The graph tells you that if you want to read, what you need to do is you need to send the read command. And we know that the read command, which is this one here. So we are reading. So the one we're actually after is this one here. So the read command, we stored it in here, and it's basically 0B. We just send it, and then the next thing we do is we send the register that we're interested in, and that's actually register number 2. And then what we do is we do transfer. Okay, and the transfer, we send the slave, which is the accelerometer, we send it a dummy data, basically a dummy byte, which is just a 0 because it's not going to read it. And then it returns some sort of a number. We're going to cast it into a signed integer, and that will be the ID. And according to specs, this should be F2. And then we deassert the slave so that we tell it like, hey, the transaction has ended. We read what we want. And then what we do is we basically just send that value that we just read into the UART so we can see it. It's similar for the others, for the X, Y, and Z. So we assert the slave select, we send it the read command, we send it the data register, which is register 8, and then we read a byte and another byte and another byte. So it's actually automatically incrementing it from 8, 9, and 10. That's the X and Y and Z. And then we deassert it to tell it like, hey, we're done reading that transaction, and then we divide it by the row max. So the X and Y and Z are not the row values, not the row 8-bit numbers that we just read. It's actually divided by the value of 1G. So this will be basically whatever is stored in X and Y and Z is actually in terms of Gs. And this is what the comment says. We send it to UART. So let's see this program running. And frankly speaking, before we send it, we did not use the LEDs, so we can definitely take these out, and we can definitely take it out from here. We're not displaying anything on the LEDs. Everything is actually being sent to the SPI. So I'm gonna just compile it and load it to the board so we can see what's the effect of doing that. So the code is now running. I have opened the UART, the terminal, the console, and as you can see, it's actually sending data nonstop, and it's very difficult to read it. And the indication that it's actually sending stuff over the UART as well, you can see it on the board, is here. That little LED here is almost always lit. it's actually always lit because it's super fast. So we need to slow it down a little bit. And the way we're going to slow it down is actually by putting a little bit of a sleep, maybe for 350 millisecond at the end of that test program. And then we're going to compile it and actually just load it again. All right, so now it's a little bit easier to read. And we can see the message here. I'm gonna just pause it. It tells me, I'm just gonna do this here. It tells me that the ID should be F2, and this is exactly what we're reading. And the values for the X and the Y and the Z are negative 0.09, about 0, and then negative 0.8. Frankly speaking, it should be, the Z should be about -1, but I think it's just depending on the position of my board, depending on the position of the table that the board is on, it's a little bit tilted. So a little bit of it is actually on the X direction, the other one is in the Z direction. If I change the board a little bit here, you're going to see that these numbers will actually change depending on where we are. It's actually detecting both static and the dynamic one. So if I leave the board as is, it's basically, this is the static, and I believe maybe if I move it that way, this is how, maybe this is how tilted my board is, or something like that, or maybe it just needs some sort of a calibration. But anyway, you get the idea. So I'm reading the X and the Y and the Z, and I can do really neat stuff with it.